Swayam Prabha. Digital India. Educated India.
Okay, so how was the quiz? Easy? How many of you felt easy? None? Hard? Raise your hand, like how many hard? This will help me set the question paper for the second quiz in end semester. If you say neutral, then I may assume something. So, easy, show of hands. Okay, no one felt, you felt easy. Okay, I'll come to moderate. Yeah, easy, who felt easy? Easy means like, you know, the question paper, five questions for 50 minutes. Let's say you finish in 30 minutes and then you're left. Anyone did like that? Huh? You did like that? Hard? How many felt hard? Very difficult. Moderate? Okay. Okay, always, okay, everyone, literally everyone felt moderate. Okay, fine. That's good. It should be like that. So it can't be hard, can't be easy. So, so I thought maybe in this lecture I will solve these problems so that you can check, you know, your answers. Okay. So the first question is very simple. In fact, it's just an extension of one of the problem I did already in the class. Okay. So we had a binary mixture then, and I showed how to calculate number average and weight average molecular weight. So it's same thing. So this should not been hard. This should be very easy, right? So you got we got sample A, B, and C. Okay, we got 3 samples. Sample A has a molecular weight of 10 power 5 Daltons, right? And sample B has 2 into 10 power 5 Daltons, and sample C has 4 into 10 power 5 Daltons. Okay, this information is given, and then mass also is given. Mass of A is 1 gram, mass of B is 2 grams, and mass of C is 3 grams. So we need to calculate the let's say the number average, which is written by sum of Ni Mwi over sum of Ni. Okay, which means here we have 3 species. We could write Na Mwa plus Nb Mwb plus Nc Mwc divided by Na plus Nb plus Nc. So what are Na, Nb, Nc? These are number of moles or number of molecules of the chains, right? So we calculate Na by mass of A divided by molecular weight of A. So mass of A is 1 gram, and mass molecular weight of a species A is 10 power 5 Daltons. Daltons is nothing but gram per mole. So basically you will get 10 power minus 5 moles. This is Na. Nb would be mass of B divided by molecular weight of species B. So this is 2 gram over 2 into 10 power 5 gram per mole. So this is also 10 power minus 5 moles. Nc is Mc by Mwc. So Mc is 3 grams and molecular weight is 4 into 10 power 5 gram per mole. So, this is 0.75 into 10 power minus 5 moles. So, we found all the number of moles, then we can substitute in this equation now. So, Na is 10 power minus 5 multiplied by MWA, that is 10 power 5, plus NB is 10 power minus 5 and MWB is 2 into 10 power 5 and NC is 0.75 into 10 power minus 5 times 4 into 10 power 5, and this divided by 1 plus 0.75 into 10 power minus 5. So, you get 1 plus 2 plus 3 into 10 power over 2.75 into 10 power 5. So, this is 6 by 2.75 into 10 power 5. So, this means that the number average molecular weight would be 2.18 into 10 power 5 Daltons. Okay. Any doubt in this? From the mass and molecular weight, you get the number of moles, and then you weigh the molecular weight with respect to the number of moles. Now, I think the question also asks to calculate the weight average molecular weight, that is MW. So, for that you need MW as sum over mass of I, molecular weight of I over sum of masses. Okay. So, for species A, mass is 1 gram and its molecular weight is 10 power 5. For B, we have 2 grams into 2 into 10 power 5, that is the molecular weight. For species 3, we have 3 grams and its molecular weight is 4 into 10 power 5, and this divided by the sum of the masses, that is 1 plus 2 plus 3. So, this is in grams and this is in gram into gram per mole. So, we get 1 plus 4 plus 12 into 10 power 5 divided by 6. So, that is 17 by 6 into 10 power 5. So, this is 2.83 into 10 power 5 Daltons. Right? Clear? So, that is the first question, and so moving on to the second question. What about this? Sample A of polyethylene is prepared with 50% crystallinity, having an enthalpy of fusion obtained from DSE as 300 joules per gram. Another sample B of PE is prepared under different conditions with an enthalpy of fusion as 150 joules per gram. Calculate the percentage of crystallinity of sample B. I think the class we looked at two ways of calculating crystalline content. One is based on this enthalpy of fusion from DSE, or based on the molar volumes of the sample and crystalline sample. So, in this problem it is based on enthalpy of fusion. Okay. So, for us the definition of crystallinity is delta H S by delta H C into 100. So, this is the enthalpy of fusion for the sample, and this is the enthalpy of the same sample if it is 100% crystalline, okay, which has to be obtained from some other sources. So, in this problem this data is not given, but we are comparing between two data. Okay. So, sample A, what is given? we are giving that the percentage crystallinity is 50% and delta Hs is 300 joules per gram. These two data are given. So, with this using this definition we can calculate the fully crystalline heat of diffusion. Okay. From here you will get delta Hs by percentage crystallinity into 100, and this would give you 300 by 0.5. Yeah, so this should be 50%, right? 50, 100. So this will give you 600 joules per gram. So based on the data given for sample A, you can get the 100% crystalline materials heat of fusion, and using this you can go to sample B. Sample B, what is given is delta Hs is given, and this is 150 joules per gram. So for this sample, percentage crystallinity is 150 divided by 600 into 100. So that is basically 25%. Yeah. How many of you got this answer? All of you? Straightforward, right? Simple. If you know the formula concept, and it's very simple in the sense. So this is again a very straightforward problem, right? It's just basically sketching the mechanical model for this standard linear viscoelastic solid. So we know that for standard linear viscoelastic solid, we would have, there is a linear spring, right, E1, and this is connected to a Kelvin arm. So there will be a dashpot, and then there will be another spring, and together they support the stress. So this is E2 and this is eta. Okay. So I have said that clearly indicate the relevant parameters. What it means is you should say for this spring the corresponding spring constant or the is E1, and for this is E2, and for this dashpot it is characterized by a viscosity eta, right. So straightforward. So if you have seen this picture, you should be able to do this. Very simple. What about this one? What answer did you write? What is the interpretation of this data? First spike is, sorry, what? Melting point. Okay, so which one? Which this spike? So this is this melting. Okay, and this is basically melting temperature, right? Melting point or melting temperature. Okay, what else? Yes, this corresponds to glass transition. Yes, this also I have given this kind of plots in the one of the so yes, it has two glass transition temperatures. Yes, both are glass transition temperatures. So when can you have such a situation? When can you have two glass transitions? When you have a mixture of two polymers, each can show its own glass transition behavior. I think in the case of ABS, we noted two glass transition temperature, but then you can also have a single melting point, or maybe more than one melting point also, depending upon material. Okay, this is just a hypothetical case, just to see that if you are presented with the DSC curve, you should be able to tell where melting is and where the glass transition is. So glass transition is a second order phase transition. Okay, so its signature is very delicate. Okay, the step change I have clearly shown, but in practical thing it may not be like this. It may actually have very shallow transitions, right, like this. Whereas melting involves absorption of heat, it is called first order transition. There is a step change in the density, there is a step change in the enthalpy. So, you will see a peak in the DSC curve. Okay. So, you have to always look for this kind of sharp peaks versus very small step change to differentiate between the TG and melting point, and TG always is lower than the melting point. Okay. So, that is the way you can interpret this particular DSC curve. What about this? How many of you solved this problem? You did? Okay. Did you get all the data for this problem? So, this problem was designed to indicate that, you know, it is in a given problem, it is not necessary that all data will be given. Some data may be missing. Okay. So, this is just to kind of destabilize you a little bit. We are usually given with the fact that, okay, data, unique set of data, there is a one single answer. Okay, that is how we think, but in reality that is not the case. Sometimes data is missing. So, this problem has some of those issues, and a similar problem, exactly similar problem we did for the SLVS model, standard linear viscoelastic solids, but here this model is for Maxwell model. So, my hope was that you will be able to take that as an example, but apply for a Maxwell model. So, that was the context. Okay. So, first we will write whatever is given. So, we have the initial length is 100 millimeters, right, and the diameter is 5 mm, and then this is subjected to an axial tensile load of 500 Newton. So, the force is 500 Newton. So, we need to find length at t is equal to 100 seconds, and some other data is viscosity is given as 10 power 3 Pascal second, and then the material model is Maxwellian. So, we need to calculate L, and then we also want to calculate the creep compliance. Right. So, this you know, the fact that I am asking creep compliance basically means is a creep test, right. That means you take a plastic, you apply a load and for a long time, and you look at as a function of time how the elongation strain develops. So, this is basically a creep relaxation, a creep response. Another possibility would be stress relaxation, where you give a constant strain and look at how stress develops. Okay. So, that is the first thing you have to decide, is whether it is a stress relaxation or a creep response. It is a creep response obviously. And then so what we need to do is for Maxwell model, what is the creep response equation? So, if you plot stress, so at time t equal to 0, we put some 500 Newton, and then it just maintains over a period of time. Okay, let us say this is t equal to 0, and this is corresponding to a load of 500 Newton. Okay. So, what is the response for the strain? How would strain respond here? You said it will start from 0. So, the moment you apply stress, what will happen to the material? It is a Maxwellian material. What it means to be a Maxwellian? What do we understand as a Maxwellian model? What is mechanical model will look like? Yes, there is an elastic component and there is a viscous component. Okay. So, the immediate effect would be elastic. So, because of elastic response, the strain will take a immediate response. Okay. So, that would mean that there is going to be a small jump, which we call as epsilon naught. So, this is immediate response of the material due to elastic nature. And what is the viscous response would be? it would increase linearly with the slope of sigma by eta. Okay. So, basically for Maxwell model, the creep response would be epsilon naught plus sigma naught by eta times t. Okay. This equation you have to remember. If you do not remember this equation, you can derive it also. You write the Maxwell model and then you say stress is constant, integrate over time, you will get this equation. We derived this equation in the class also. So, now epsilon naught, what is epsilon naught? What is the elastic response would be? Yeah? Yes, stress by Young's modulus. Can we calculate stress? We can calculate because this is force by area. Force is given, this is 500 Newton, area, cross section area is pi by 4 d square. So, this is 500 into 4 by pi into 5 square in the units of Newton per mm square. So, that is basically 80 by pi Newton per millimeter square. So, this is a stress, this is actual stress that is applied to the material. But to calculate this epsilon naught, you also need Young modulus, and Young modulus is not given. So, you have to keep it as such. So, epsilon naught has to be simply epsilon naught by Young modulus. Unless that is mentioned, you cannot know what is epsilon naught. Okay. So, you have to keep that as a parameter. Okay. Now, the second part. So, this can be calculated directly because sigma naught we know, viscosity is given, time is also given, right. So, if you look at this part, sigma naught by eta t, this would be 80 by pi into 1 by 10 power 3 into 100 second. Okay. So, if you do that, you will have problem because the stress is given in the units of Newton per millimeter square, whereas viscosity is given in Pascal second. Okay. So, Pascal is nothing but Newton per meter square second. So, second will get cancelled, Newton will get cancelled. So, you have meter square here and you have millimeter square here. Okay. So, what you need to do, you need to multiply this by a factor of 10 power 6 to convert this into meter square. So, I am going to just remove this, write as meter square and divide by 10 power minus 6. Okay. Otherwise, you have unit inconsistency. So, what do we have here? We have 8 into 10 power 3 by pi into 10 power 3, minus 3. So, this would be 8 by pi into 10 power 6. This is going to be a non-dimensional unit, right. So, now we have epsilon, that is 80 by pi into 10 power 6 by E. So, this is your epsilon naught plus 8 by pi into 10 power 6, and strain is a non-dimensional quantity. Okay. So, you have to make sure that everything tallies with a non-dimensional quantity. What should be the unit of E here? Pascal. Okay. It has to be Pascal. And if you want to substitute in terms of megapascal, then you have to remove this 10 power 6 term. Okay. So, make sure the units are consistent. So, right now we cannot do anything with the first term because E is not specified. So, you have to keep that as such, whereas this one is 8 by pi into 10 power 6. And then the question is to calculate L at a time t is equal to 100 seconds, right. So, epsilon is nothing but L naught minus L by L naught, and this is equal to epsilon naught, which is unknown, plus 8 by pi into 10 power 6. Okay. So, from here you solve for L, because L naught is given as 100 mm. Okay. So, that would be your length at time t equal to 100 seconds. And the second question is to calculate the creep compliance. So how do we define creep compliance? Epsilon by sigma naught. Okay. So what is epsilon? Epsilon is epsilon naught plus 8 by pi into 10 power 6, and this you divide by your stress is how much? 80 by pi into 10 power 6. So J is going to be is it correct? Stress is 80 by pi Newton meter square. So this is going to be in Pascal, and so here we have yeah, correct. So it's going to be 0.1 plus pi epsilon by 80 into 10 power 6. Okay, so this is your creep compliance. So once Young modulus is given, you can calculate epsilon naught and you can substitute and then get creep compliance. How many of you did like this? You took epsilon as 0. Okay. What would that mean? What would that mean when epsilon equal to 0? What would that mean in terms of Young modulus? Yes. So if the material is infinitely large, infinitely strong, so that's okay. If you take E is infinite and take epsilon naught equal to 0, that is also fine. The point is not get the right answer. The point is to see how do you manage such a situation. So some people have taken, okay, I will take E as infinity and epsilon naught is 0. So you will have J equal to just 0.1, and similarly for the L also you will get that, right? What else did you think about this? But why would you do that? Because that is for a Newtonian model. Here it's very clearly mentioned it's a Maxwellian model, right? Okay, we'll discuss that later. But it has to be, so that's what I'm saying. It's very important to know what is the model that we are using. Okay, Maxwell model will have a different response, creep response. The SLVS model will have totally different response, and that 4-element model will also have a different. So it's very important what that model signifies the property of the material. Only then we can go ahead with this. Any other thoughts in this problem? Did you think this was a physically relevant problem? Why? Huh? Yes. You're very likely that the material would have undergone some sort of rupture. You can't have, typically when you look at elongation at break, 1000 is probably maximum you can hit. So you're here already, you're going 10 power 6, so it's not going to happen. Okay, so this happens when you try to take the same problem from one model and apply for another model. So okay, this may not be a physically relevant situation. Okay, so so these are the things you should think about it. Just not look at only problem or number, what it means, what are known, what are unknown, what do you do with when things are not known to you. Okay, and this is how you handle it. Okay, I think that's all. We have 5 problems only, right? So do you want to share any other difficulty you went through the quiz? Anything else with regard to the problem or with regard to the solution methodologies? Okay. So now can you take this problem and do it for SLVS model, this problem as a follow on in the class right now? Just replace this Maxwell model with the SLVS model.